internationally, we're very much in favor of this community science sort of ethos. And so right here on the title slide, everything that I'm going to talk about is open source. It's all available under, everything that I'm going to talk about is available under our GitHub repository. You can go and get the code and the data, and really with just a few clicks, almost very little effort, you can run almost any of the experiments that I'm going to talk about. There's one exception that I'll point out when we get there, but everything here is open source, and there are lots of contributors. So right now I'm at Google Research doing flood forecasting and flood model development, and using a lot of the infrastructure that we're going to talk about here. And we also have partners that are involved in some of the research that we're going to cover from Upstream Tech, which is a small data science company in the energy sector, and who's running these models operationally, or models similar to these operationally, and sort of selling them to customers in the hydropower sector. So we have experience sort of moving these models from research to operations. And then part of this research was funded by the NOAA Office of Water Prediction through a cooperative grant while I was at the University of Alabama working with the National Water Center, and we'll get to some of that work in the middle of this talk. So I'm really just a spokesperson for a whole lot of people that have put effort into this and collaborated on this over several years. And I'm going to give you sort of a technical understanding of what we've done and where we started and how we got to where we are. But this is really just really the message that I want to give here is that that when big teams come together on these AI projects, you can make a lot of there's a lot of room for advances. There's a lot of low-hanging fruit in this sector right now. Okay, so basically the infrastructure that we've been working with are these long short-term memory networks, and I'm sure that some of you are familiar with this. If you had an iPhone in your pocket in the mid-2010s, you had a long short-term memory network working underneath Siri to understand what you were telling Siri and help Siri understand what you wanted from your voice commands. That's been replaced by different types of deep learning networks now, but long short-term memory networks are basically recurrent neural networks. They have a sort of a complicated structure of neurons inside of them, represented by this block diagram here, and then they repeat, when you predict with these networks, they repeat this structure over through time. And so every repetition of this structure of gates and little neural networks represents one time step in a prediction sequence. And we really like long short-term memory networks for hydrological forecasting problems and for physical modeling problems in general, because they look a lot like PDE solutions. So they look a lot like solutions to systems of differential equations where we have a state space that we want to model. So like dx dt is equal to some function of integrated fluxes across the control volume boundary. So long short-term memory networks may be a little bit difficult to see from this diagram, but they have a state space that they carry with them in time. So you'll have a value of some hidden state of the system at time t-1, and some neural network magic will happen to affect the value of that state. And you'll have a new value of the state of the system at time t. And sort of the things that happen in the middle are one neural network that controls the memory of this, the memory timescales of this system. So a neural network that says, well, forget what happened in the past more quickly, or forget what happened in the past, remember, be more likely to remember what happened in the past for longer periods of time. They have an input gate structure, which sends information from boundary conditions into the states, and that's very much like in a watershed, that's very much like the transfer of information from precipitation to watershed, like soil moisture or vegetation water content. And they have an output gate structure, which sends information from the storage states to the output. So if we want to predict stream flow, which is a simple rainfall to stream flow, is a simple modeling problem in terrestrial hydrology, then the state of the system will contain information about how much water is in the watershed at any given time, and then the stream flow that comes out of that watershed is dependent on both precipitation and the amount of water. And so there's a direct sort of very, very similar conceptual similarity between the structure of a long short-term memory network and the way that we usually conceptualize the dynamical physical systems, including watersheds. And I just want to emphasize this because when you start to develop, there's a whole world of machine learning architectures, and it's impossible to be an expert on all of these. But what's really important is at least having some understanding of the options available, and making a direct connection between the type of machine learning architecture that you want to use and the type of problem or system that you want to work on. So I see a lot of papers, and not, I don't mean to be critical too early in the presentation, but I see a lot of papers in my own discipline of master review papers where people are interested in trying new network structures. They say, well, I'll take two deep learning architectures and apply them to the same problem and see which one works better. And that's cool, but really what translates into success in my experience is really understanding your problem and really understanding your network architecture and options available to you from the theory of AI theory and AI machine learning, and really understanding how these things couple at a deep level. And what that requires is cross-disciplinary collaboration. So the successful teams, in my experience, both in proposal review panels and just watching what actually works in literature, are teams that have experience in both worlds. So it's very easy for an earth scientist to say, oh, this is a new statistical modeling technique. I'm gonna go to the literature or the blog post and kind of pick some, or to the TensorFlow or PyTorch documentation and kind of pick some of these models off the shelf and apply them to my problem. And that's not really AI. That doesn't work. So AI is actually, at least the theory of AI is at least as deep a subject as sort of all of earth science combined. And the idea that we can sort of treat this as a set of tools that we can pick up and apply to our problems is a little bit, just a little bit naive. And so what really needs to happen to make these things, to capture sort of the phenomenal power that we're seeing in AI development recently in our individual domain sciences, are real cross-disciplinary collaborations. We have to have real computer scientists that are leading the discussion about how to use AI in domain problems, and we have to have earth scientists that have a real literacy in machine learning, but of course not an expertise, because no one person can be an expert, and both subjects are so deep that it's impossible to be an expert in both. Okay, and so you can embed this kind of architecture. So we're going to talk about rainfall-runoff modeling. We like LSTMs because they look like dynamical systems. They have an input state output relationship, just like almost all hydrology models that are currently in use around the world. And so we can embed this sort of LSTM time series structure into a larger deep learning network, and we can do that for a variety of reasons. We can have embedding layers that take in different types of input data, remote sensing data, mapping data, human data, data about anthropogenic influences on watersheds, and data about characteristics of watersheds that come in different forms. And what you'll do is you'll choose in different embedding layers depending on the type of input data that you want to use, but you can sort of stack these in series and parallel as inputs into your time series model. And then on the output side, we might want to predict a whole bunch of different things. Like we might want to predict network structures of rivers. So these are convolutional. These are going to use convolutional filters that have non-regular topographies or geometries, so graph convolutions. We might want to predict probabilities, in which case we want to use probabilistic network structures as outputs. And the point that I want to make here is that you might have certain parts of your problem that are similar, and we can train an LSTM on very simple parts of the data, and then you embed that trained model into a larger deep learning network using transfer learning techniques or other types of techniques, depending on what our specific goals are. And so there's, again, each one of these little things that we might want to do is sort of a body of research, a research project for a student or for a postdoc or something. And then at the end, the goal is to have a sort of a flexible deep learning structure that can do a lot of different types of things. So all of the experiments that I'm going to talk about for the rest of the presentation today basically work like this. We're going to talk about a very sort of portion of the hydrological modeling problem, which is taking rainfall and turning it into runoff. I want to kind of give you an idea of what can come out of this sort of very simple problem set. And basically the experimental setup that we're going to talk about for the rest of the presentation is this. We're going to take dynamic meteorological conditions and forcing data, that's like precipitation and temperature and air pressure, and we're going to take static catchment attributes about climate indices, geology, soils, vegetation, topography, different descriptors of catchments, and we're going to feed those into a time series learning model that has something that looks like an input state output relationship. And we're going to do that across 531 basins in the United States. This CAMELS dataset, which is a large sample hydrological dataset, community dataset that was created by INCAR and is available to everyone, and it's sort of de facto become sort of the one of the, like the MNIST of hydrology, the standard data set that people test models on in hydrology. And so we have about 9 years of training data. We're doing daily predictions, et cetera, et cetera. There's a lot of catchments in the CAMELS dataset, so 531 catchments across sort of a array of different ecoclimates. So we have different precipitation, different geologies, different pedologies, soil structures, different climates, different vegetation types, different rainfall patterns. The seasonality of rainfall is different. And so all of these things affect how a hydrological model will behave. And to date, before deep learning came along, the best hydrological models in the world would be calibrated to an individual catchment. And that's because the geologies and the soils and the vegetation, topography, seasonality, climate, all these things affect the way that a model, an optimal model should behave in such large ways that the best strategy for making the best possible hydrological predictions was to have a long data record in a specific catchment and calibrate that model to that specific catchment. It's not always possible, but that's how you would get the best predictions. Instead, what we do is we take one deep learning model and we train it over the whole country. So we have one LSTM model that we deploy, we train over all the data that we can get from the whole country, and then we deploy it on all of these watersheds across the whole country. So that's the first benchmarking experiment that we're going to do. So we have data from all the 531 catchments. We split the data record into training and testing splits, and we validate on the test split. And this is sort of the results. So we benchmarked against a whole bunch of hydrology models. So we went out to the hydrology community and said, anybody that is willing, please submit your runs of your models over this sort of standard community database. Most major hydrology groups in the world have already done this before we came along, because CAMELS is sort of this de facto benchmarking data set, and then contribute that to our GitHub platform, and we'll sort of create statistical analysis of this. And so we had the hydrology community run these benchmark models, and a whole bunch of people gave us models. And so the deep learning models are in orange and green here. These are CDF plots. You want to be as far to the right as possible. This NSE is like an R-squared statistic, so you want to be as close to 1 as possible in as many basins as possible. So this is the fraction of 531 basins on the y-axis. So we have orange and green are the LSTMs, different LSTM structures, and all the other colors of models, lines are different hydrological models that contributed to the benchmarking analysis. And so if we look over here at the right plot, these are the benchmarking models, the standard hydrology models that are calibrated individually to each basin. So they can't be applied to any basin where you don't have long data records. And then they're benchmarked against an LSTM that's seen the whole country, one model seen the whole country, made predictions over all the basins. And it's interesting that we can calibrate a model to a deep learning model to all of the basins, not to specific basins, and we actually do better than the traditional hydrology models calibrated to individual basins. This is exciting because one of the hard problems in hydrology is how to make predictions over large scales without having to calibrate in every basin. And so deep learning sort of does this. There are ways that hydrologists sort of try to do this. They take data from all of the basins and try to try to map parameter sets. This is called regionalization or regional calibration. And so this left plot benchmarks against a few groups that have implemented those types of strategies. And you can see they always result in a little bit of information loss. So these traditional models are always just a little bit worse regionally calibrated than locally calibrated. Okay, but the real problem is we want to predict in basins where we don't have stream gauges. And so these are the results from doing that. So we're comparing against the National Water Model from NOAA here, the reanalysis, which is hosted on the Amazon through Amazon Web Service. It's publicly available. We went and downloaded those predictions, and we benchmarked against those predictions. And we also benchmarked against the Sacramento Soil Moisture Model, which was calibrated by NCAR, so calibrated by a group that has a lot of experience using this individually to each basin. And so that's our benchmarks are the orange and the blue line here, and the purple line here is a deep learning model that was calibrated on different basins than it was used to predict. So you split the country up into some number of k-fold splits, train on k-1, and then predict on the last one and repeat that experiment. So every basin gets predictions from models that were trained on only other basins. Okay. And as opposed to the orange line, which is the Sacramento model, which is calibrated individually for every basin. So you have to have long data records in each basin to get as good as this orange line. Whereas the purple line works in basins where you don't have any data. And so not only does deep learning provide better predictions in basins where it's seen data, but it actually can go to new basins and on average provide better predictions than sort of the best hydrology models that exist can provide in basins where there are long data records. So this is the problem of prediction in ungauged basins is sort of one of the most famous named problems in hydrology. And deep learning can do better against that problem than traditional models can do, even without considering that problem. That's a huge advance in hydrology. It allows us to, for the first time really ever, we have the potential to go and make semi-accurate forecasts in basins that don't have gauge records. And so this is important in developing countries, which is where, for example, Google is interested in, through their AI for good flood forecasting effort in countries where there isn't a lot of hydrological data. But it's also important in the United States, because in the United States, the National Water Center makes predictions at 2.x, I think it's 2.3 million locations, but we only have gauge records at any point in time from 18,000 of those locations. So the vast majority of locations that we want to make stream flow predictions, even in the US, which has a really dense gauge network, the vast majority of those are ungauged. Okay, the other interesting thing about these deep learning is that it does better when you give it more data. So that's obvious, but it's not obvious in hydrology, where the best predictions come from calibrating to individual basins. If we actually get better, deep learning actually gets better results when it sees all of the data that you can give it. So when the solid line here, again, further to the right is better. The solid line here is one model trained over all of the data from the whole country. And the dotted line is where we've spent a lot of time. We've hyperparameter tuned. We've not only trained, but we've tuned the hyperparameters of an LSTM individually for every basin. So with one basin, we've tried to do as good as we can in that basin and really spend a lot of time with each one of these 531 basins. That's the dotted line versus the solid line, which is where we just take one model, throw it at the whole country and see how good it does. It's in just orders of magnitude less in time investment, and we actually do better. And the reason for that is that these deep learning models are really learning how they're developing some sort of internal representation of hydrological processes. We have some papers on looking at that internal representation, and I don't want to get into it now because it's kind of technical, but we're using techniques from explainable AI to kind of understand how the model is learning to learn from one catchment and transfer that knowledge to another catchment. But again, I just want to point out that this is really a first in hydrology. This is something that hydrologists have struggled to do for a long time, even with these same data sets, train in one basin and predict in another basin. And we're seeing that deep learning sort of not only does it naturally, but gets better when you approach the problem that way, and does it with very, very little effort. So much less effort than it would take to deploy a model basin specific. So a lot of tasks that we want to do in hydrological forecasting become very easy with deep learning. So probably most of the hard tasks in hydrological forecasting become very easy with deep learning. So here's one where we're using multiple forcing products. So the atmospheric scientists give us rainfall predictions, which are our boundary conditions for the the watershed system. So we're producing stream flow from rainfall predictions or estimates or forecasts. And since there's high uncertainty in the precipitation estimates, we typically want to take ensembles of precipitation forecasts. And that requires fancy ensembling strategies usually. But with deep learning, you just throw all of the ensembles in as an array of inputs into your deep learning model, and the model itself learns how to combine these. And so I'm not going to go into the CDF in detail, but the bottom line is that we get almost as much improvement by giving multiple forecast precipitation products. We get, again, about as much improvement as deep learning improved over regular hydrology models by itself. So there's huge benefit to doing this in terms of improving accuracy. And what the deep learning model here is doing over here on the right, the different colors represent sort of the most important. This is, again, one model trained over all the data, the same model for every basin. Each dot is a different basin, and each color represents which of three particular forcing precipitation products the model chose to pay the most attention to. And we can see one model kind of learns in different places around the country and wants to pay more or less attention to different different precipitation products, and even during different parts of the hydrograph. So whether the stream flow is rising or falling, or whether it rained 1 day ago, 2 days ago, 3 days ago, the model is going to learn to pay attention to different precipitation products. So it's a highly nonlinear model, and it kind of, if you give it enough data, it can learn how to use these products effectively in nonlinear and non-stationary ways. We can predict at multiple timescales. So this is again a benchmark against the National Water Model in orange, and a bunch of different types of LSTMs in the other colors. And again, we do better than the National Water Model by quite a bit, but that's not really the most important story here. The most important story here is that when the National Water Model makes daily predictions, usually hydrology models get better when you aggregate over time. You get better, statistically better predictions when you average a bunch of short time scale predictions. You kind of average out some of the uncertainty. This is a phenomenon everybody's probably familiar with. So we're making daily predictions in the solid lines and hourly predictions in the dotted lines. And like all hydrology models, the National Water Model gets a little bit worse when you talk about hourly predictions rather than daily. That phenomenon does not occur in deep learning models. So the deep learning models are really able to take hourly training data and really learn the hourly behavior as well as they're learning the daily behavior. So not only do we get a bump in improvement using deep learning as compared to the National Water Model, we don't lose any accuracy by moving to hourly time steps. So we can give people hourly flood forecasts rather than daily flood forecasts, which in flood forecasting daily is not that useful. And we can do that with sort of the maximum possible accuracy that we can get. And again, that's just because these models are really able to they're really good at extracting information and patterns from data, and they're apparently, this is an empirical result, but they're apparently as good at extracting short time scale pattern hydrological information as they are at longer time scale, rather than this phenomenon of sort of where it helps to average over uncertainty. So we actually use different models or sort of deep learning models with sort of deeply embedded connections that actually make different predictions hourly and daily. And then we use regularization in the loss function to make sure that the hourly forecasts, that the hourly components of, again, they're deeply embedded by sharing embedding layers and things like that in the deep learning architecture. The hourly and daily models are, but they give separate predictions. And then we use regularization techniques to make sure that the hourly predictions agree with the daily predictions and things like that. There's a paper on arXiv right now that explains all that. We can do remote sensing data assimilation with almost no effort. So data assimilation in hydrology is hard. You have to use things like Kalman filters or other types of inverse techniques, and it takes a long time to set those up. So my background in the NASA modeling team was developing data assimilation systems, and it would take a good 6 to 12 months to set up a really robust data assimilation system for a new satellite. In deep learning, these results from assimilating MODIS vegetation data took probably 48 hours worth of effort to implement, whereas again, it would have been about 6 months or a year worth of effort to design the data assimilation system. In a traditional hydrology model, these were done incidentally by Upstream Tech, Alden Sampson at Upstream Tech, this private company that's doing this in the private sector. Basically, the strategy is you just take whatever satellite data you want to use, then you take it as inputs into the model. There's a few more complicated strategies on how to do that, but this works just as well as anything. And again, it's just several orders of magnitude less effort. And actually, we have some work that's in preparation for being published here, but it actually gives better predictions than inverse methods like Kalman filters and variational filters, which necessarily, due to the parametric assumptions in these models, necessarily lose some amount of information. The deep learning networks, which are highly nonlinear and highly non-parametric, are able to extract a lot more information out of the remote sensing data with a lot less effort. We can do a probabilistic forecast. So instead of using ensembles to develop probability distributions over stream flow, we can actually just ask the deep learning models to predict probability distributions rather than to predict stream flow itself. We have a paper coming out that's led out of Johannes Kepler University that's just about ready to be submitted, where we compare a whole bunch of probabilistic deep learning models to produce probability distributions, but the end result, to sort of spoil the result, is that they're almost statistically perfect in the long run. So this particular model was developed by Alden Sampson at Upstream Tech to provide hydropower customers not only with predictions of inflow into their reservoirs, but to provide probability bounds on those. And basically what Alden does is he has the deep learning model predict mixture distributions or histogram distributions that aggregate to sort of non-symmetric, non-Gaussian probabilities. And so instead of having the network predict stream flow, it's predicting parameters of mixture distributions. And then the loss function for training is a likelihood function. Okay, and so it's really easy to make the models predict uncertainty, whereas in traditional hydrological modeling, you'd have to run many repetitions of the model and treat those as samples from a probability distribution. And it's very, very computationally expensive. And it's also a hard Bayesian probabilistic problem to do it well. In this case, it's very, very simple, and it can be done. It really just takes, it's really a matter of hours to set up something like this that's extremely accurate. Okay, so how am I doing on time, Kayla?
We've got about 10 minutes left, including questions.
Okay. Yeah, so I'm just going to say one more thing, and then I'll stop talking. So one of the things that we lose when going to deep learning, just straight deep learning, like again, we're using the same models that were previously used in your iPhone to work with voice recognition in Siri. So there's really no, and you can make the case that they look like dynamical systems models, but there's no physics in these models. So really the big research question that I see on the horizon is for not just for hydrology, but for the whole of earth science and integration with AI, is how do we understand, how do we really tackle the knowledge-guided machine learning or physics-guided machine learning problem? So there's a lot of people working on this. It's still probably, in my view, the largest open problem. We've done a little bit of that work. This is the work that was sponsored by Office of Water Prediction and NOAA, where we took the outputs of the National Water Model and fed them in as inputs to the LSTM. And in the interest of time, I won't go through these CDF curves, but the bottom line is that of course, the LSTM in blue and orange does better than the National Water Model, but adding the National Water Model input, which is orange versus blue, doesn't actually improve the prediction. So we're not actually getting, if we take just the simple strategy of taking the outputs from a physically based model and putting them into as inputs to a deep learning model, in this particular case, this particular domain, actually doesn't provide any value. It's interesting, we can go and look at what inputs, what states and fluxes from the National Water Model are actually being used by the LSTM. So this is sensitivity analysis on the inputs. Blue are states and fluxes from the National Water Model, which are being given to the LSTM as inputs, and orange are the regular meteorological boundary conditions that all of our LSTMs have used so far. And it's actually, the model actually is sensitive to some, it is learning from some of these National Water Model states and fluxes, specifically from stream flow and the stream velocity and some base flow, snow equivalent. It's actually learning from these things, but it's not producing better predictions than without them. So what this is a hint, at least, that the LSTMs are really able to extract a lot of the sort of, let's call it, physically based information from the data that you're giving it. It also shows that this is a really naive way of integrating physics into the machine learning models, but maybe there's something, we know the National Water Model has high uncertainty associated with it. We know all hydrology models have high uncertainty. So maybe there are ways that we can take certain pieces of these our physical understanding of watersheds and sort of use certain pieces that we're really confident about to improve predictions. And of course, the thing that we're most confident about in hydrology is mass balance. So LSTMs look like they have input state output relationships, just like, but they don't conserve mass or energy. So the project that we're working on now that we just submitted to the latest NeurIPS workshop, or the NeurIPS workshop in December, is embedding conservation laws into deep learning networks that look like LSTMs. Basically, I'll skip the sort of the deep learning theory here, but basically we can come up with an LSTM-like structure where all the gates, the input gates, the output gates, the memory timescale gates, all of the components of the LSTM are designed in such a way that they have normalization layers and summation layers and different standard deep learning components arranged in a particular way such that they can never violate mass balance. So the amount of rainfall that comes in is always represented by a summation of the state values, that's the storage in the system, plus a summation of all the history of the outputs. And so we can this way we can embed the physical laws that we're most confident about into the deep learning network architectures and give us a platform for testing potentially testing more nuanced pieces of hydrological understanding. We get slightly better predictions by doing this, only very, very slightly. Embedding conservation laws into the deep learning, into the LSTM gives us only a very, very tiny, still statistically significant, but very, very tiny improvement in R-square score, but it really gives us a fairly strong improvement in predicting peak flows. And that's because peak flows are rare in the data record. The LSTM is only going to learn to match peak flows, whereas the mass conserving deep learning model has to do something with any water that you give it. So if you give it more water than it's ever seen before, it has to do something with it. So it's going to push it out into stream flow, even if it's never seen stream flow that high. So we really get improved predictions for flood forecasting using these mass balances. And we can look at the internal states by enforcing mass balance across a deep learning network, and you can do this in any type of deep learning network. We've done it in these recurrent time series neural networks, but enforcing mass balance across these networks means that all of a sudden the hidden states of your network are labeled with physical units. We don't have data associated with them, but every state in the model now has a physical unit associated with it. And so we can kind of take some of those units that have millimeters. All of our water data is in millimeters. And so some of the hidden states in the model have units of millimeters. We don't know what they represent, but we can start to explore that. So here's one example of that, where we've taken some of our states with physical units and just summed them up, just taken 4 of the 64 states in our LSTM and added them together. And that's the yellow line here, and we've compared it against observed snow in one particular catchment, and that's the blue line. And so we can kind of see that when we add physical units to the hidden variables in the LSTM, that it's kind of learning that, in this case, to reproduce snowpack. And again, this model was not trained on any data related to snow at all, just precipitation, temperature, and runoff in the stream. And yet it still kind of learned to reproduce the snow state in these catchments overall over all the 531 catchments with a correlation coefficient of something like 0.8 to 0.9. Okay, and so I'll just leave this slide up. All this work is really a collaboration between a huge number of people across the world, and really appreciate the opportunity to share it with you. Thank you.
That's great. That was really, really interesting. I feel like I have learned more on this webinar than I have in a while. So I appreciate it.